Good morning, sir.
Good
Morning,
morning,
sir.
sir.
Am I audible?
Yes, sir.
Yes, sir.
Okay, sir. I think we should start now. Mm, to start with, first I shall give you the syllabus of this part of high voltage engineering. So straight away, I am going to present the syllabus before you. After you take down the syllabus, then we shall start our discussion on the particular topic. We shall start with the first chapter. This is the syllabus. I shall wait for some time. You just take down the syllabus as fast as it is possible.
Can we move to the next slide?
No, sir.
Huh?
Sir,
Should I wait for some time?
yes, sir.
Voice is not clearly audible. Okay. Now, can we move to the next slide or should I wait for some time? Okay. ক্লাস নিচ্ছি, পরে কথা বলছি।
Sir, will you give us those documents in PDFs?
Yes, I shall provide. I shall provide the topic-wise class notes.
Okay,
That I
sir.
shall do. Okay. So is it finished?
Yes, sir.
Okay, so let us move to the first chapter. Let us start our discussions. So we start with our chapter 1, and the first topic. And the first topic will be advantage of high voltage power transmission and distribution. So you all know the best combination for transmitting power from one place to another place is high voltage and low current. Now these things I know I think why it is why this combination of voltage and current is selected is already known to you, but let us very fast recapitulate or brush up the particular thing once again. Now here on the first slide you see that 3 points have been mentioned. First of all is this: generator are located at a place. Normally, what happens? The power system, the power stations, we should say, the power stations are located at a place which is not really very close to the place where the load is actually consumed. In other words, normally the distance between the generating stations and the load consuming centers are quite far off. The distance is quite long. That is why you have to transmit the power over a long distance, and that is why most economic mode for transmitting power is always short up. Next is this. Another thing is this: normally the power is transmitted to three-phase system, not instead of single-phase system. And in the case of three-phase system, the number of conductors required will be 4. As you know, three-phase 4-wire system with earth wire is normally utilized. But had it been 3 single-phase systems in place of three-phase 4-wire system, then the number of conductor requirements would have been 6 in place of 4. That is why three-phase 4-wire system is selected. Now we shall continue our discussions in connection with a very simple three-phase 4-wire system, and that is shown in the next slide. here we are considering a very simple three-phase four-wire system, and you see the phase and line voltages have been shown in your figure. These things are all known to you. Again, transmission loss will be, if I is the current, then 3I square R will be the transmission losses in the three lines. Now, normally during power transmission, a fraction denoted by X is assumed, and this, what is that? That is nothing but the permitted fraction of transmission loss. And it is defined by the ratio between the power loss under rated load to that of the power supplied or rated power supplied. So that is X. Normally in power transmission, this X is specified. Again, we know that total power transmitted is expressed as 3 V phase I phase cos phi or 3 VLIL cos phi, and the transmission loss 3 IL square R. Now, if we substitute IL in terms of voltages, etc., voltages, power, etc., we can write the expression like this, and finally we can simplify the expression and we arrive at this. That is, transmission loss is equal to P square, where P is the power, into rho into L by A whole divided by VL square cos square phi. I think you just have a look on this expression. I think there will be no difficulty in understanding this expression for transmission loss, total transmission loss. Is it okay?
Yes, sir.
Okay then. Next, you see that L is the length of the transmission line and A is the cross section. In the previous expression, obviously, L is the length of the transmission line and A is the cross sectional area of the line. Now, from the above expression, we can find X as follows. X is equal to transmission loss by rated power. So, transmission loss, we substitute for transmission loss the expression we had in our previous slide, and P is the total power. Therefore, the expression for X finally becomes P into rho into L by A VL square cos square phi. Let that equation, that number is 1. So, is it okay? This X here. Or should we go back to the previous slide to show you the expression for transmission loss once again?
No, sir, it's okay.
Okay. Then we move to the next slide. Therefore, A is equal to, from the previous expression here, we have the expression for X. From here, we can find out the expression for A. A will be obviously P into rho into L by X VL square cos square phi. That is what is written in the next expression. So, this is the expression for cross-sectional area of the conductor, and that is equal to P rho L by XL VL square cos square phi, and that number of the equation is 2. Now, the total volume of copper will be P into AL, AL being the volume of copper or volume of the copper of the conductor in one phase or one line. Then the total number of conductors will be 3 into A into L for 3 lines. Now the total volume of copper is 3 into P into rho into L square by X VL square cos square phi. From equation 2, that we can write total, just multiplying this by 3. Now from the expression of the volume of copper, it is clear that the transmission voltage VL is increased if the transmission voltage VL is increased from this expression, obviously. Volume of copper will decrease. And if we can manage to decrease, if we can somehow manage to reduce the copper requirement, or if we can manage to decrease the volume of copper, then obviously the system cost will improve. So that is obvious from the expression 2. Since the volume of copper is varying inversely with the square of the voltage, then increasing the system voltage will actually reduce the system cost by reducing the conductor cost in particular. So this is the reason why we go for high voltage transmission. And obviously what really happens, since over the particular distance of transmission, fixed amount of power is transmitted. Therefore, if you increase the system voltage, obviously the current will be reduced. It is VI cos pi or 3 V phase I phase cos pi, whatever. So if, or root 3 VL IL cos pi. So if that is fixed and VL is increased, obviously IL will decrease. But and there is a point that though increasing system voltage reduces the system cost by reducing the copper requirement, but we cannot indiscriminately increase the system voltage. There is some limitation that we shall discuss, but before that we should discuss some more advantages what we get when we increase the system voltage. So the advantages, these are the following advantages. With the increase in transmission voltage, the size of the conductor is reduced, that we have seen. Now for the same power to be transmitted, with the increase in transmission voltage, line current is reduced. And when the line current is reduced, obviously the line losses will also be reduced. So that is another advantage. Now lower current at higher voltages reduces the line drop, and obviously thus better voltage regulation is achieved. What is voltage regulation? Actually, it is the ratio between the change in voltage from sending end to receiving end divided by the sending end voltage. Into 100, that will give you percentage voltage regulation. Now, if the drop taking place over the line impedance decreases, obviously the difference between the sending end and receiving end voltages will also decrease. Therefore, we shall get better voltage regulation. So that is another advantage of using higher voltage during transmission. Also, since the line losses decreases due to reduction in current for the same power transmission, when the transmission voltage is increased, the line currents decreases, and thereby line losses also decrease, and reduction in line loss actually increases the transmission efficiency. That is the next point. Now, these are the limitations of increasing system voltage. So, in the previous slide, we have seen that there are several advantages of increasing system voltage during transmission. But even then, we cannot indiscriminately or increase the system voltage or transmission voltage, because increasing the transmission voltage beyond a certain value actually causes some difficulty, or it creates some disadvantages. The first thing is this: when you increase the system voltage, insulation requirement of the system becomes more. or it increases. The insulation requirements of the system increases with the increase in system voltage. So increased insulation cost somehow compensates the economy that or the gain in cost due to reduction in volume of copper. So that is somehow compensated due to the increase in uh, insulation cost. That is one thing. Now again, you all know that for any live conductor, depending upon the voltage at which the conductor is being operated, some clearance, adequate clearance from the ground objects has to be maintained. It is also valid or obvious in the case of transmission lines also. So when the transmission system voltage is increased, then what happens? I mean, the clearance from the ground objects should be increased at the same time. Now, what is the net effect? You have to make clearance from physical ground more, which means you require taller transmission tower structures. Therefore, if you have to make the tower taller, then what will happen? The cost of the tower will increase. That is one point. Also, all of you have seen that the transmission lines are suspended with the help of suspension insulators from the tower cross arms. Therefore, there is a clearance between the tower body and the transmission line. When the system or the operating voltage increases, the clearance between the transmission line and tower body has also to be increased, or it is required to be increased. As a result, what all you have to do, you have to make that tower cross arm longer, and longer tower cross arm will also increase the tower cost further. Therefore, just a minute. The tower cross, therefore, the tower will become costlier. So, these are the reasons for which, just a minute. Sorry. Now, what we were discussing is this, that why we cannot indiscriminately increase the system voltage, though operating when the operating voltage or transmission level voltage is increased, we gain in economy. But even then, we have seen that if we go on increasing system voltage indiscriminately, then as a result, or beyond a certain value, due to some reasons which we have just now discussed, the gain in economy due to reduction in copper is compensated. Now, next there is a curve which shows the way we can find out the optimum voltage level. Now, this is the insulation cost, which varies linearly with the transmission voltage, and this is the copper cost, which increases with the square of the transmission level voltage, the intersection, and this is the total cost, total system cost, copper cost, and the insulation cost, that is obtained by superimposing point by point these two costs together pointwise. I mean, at different points, adding the ordinates, we get this curve, and this is the optimum system voltage. Now, if the transmission level voltage increases, the copper cost will shift towards right. And what will happen? The first point here is mentioned that if power increases, curve for copper cost shift towards right, and so does the voltage for minimum total cost. So when the curve shifts here, the optimum voltage also shifts towards right. And if the length of the transmission line increases, the conductor cost increases, and so the insulation cost. Obviously, if the length of the transmission line increases, then obviously the copper requirement will increase, also the insulation requirement will increase. As a result, the curves will shift and a new location for finding out operating voltage or the optimum operating voltage is of curve. Now, this is something which earlier people used to find out the position. Of course, not. I should not say find out the value of the optimum level voltage. But nowadays there is an empirical relationship which is more often used to find out the optimum voltage level, that is V is equal to root over of L plus load in kVA by 150 kV. Well, L is the length of the transmission line in kilometer. So this is the, or these are the this is the discussions in connections with the advantages of transmission, advantages of increasing the transmission voltages or transmitting power at higher voltage level. Next, we shall discuss advantages of DC high voltage transmission. But before that, I stop here for 2 minutes. You just, I mean, I'm waiting for your response. If you have any questions, you can ask me. Otherwise, we shall start discussions of on next topic. So can we start our discussion on the next topic, that is advantages of DC high voltage transmission?
Yes, sir.
Okay. So at the beginning of this topic, we should say that, or we must, we must understand that power transmission with high voltage DC provides lot of advantages. But even then, because of serious and major disadvantages. High voltage DC power transmission is not very popular even today. We shall discuss the advantages and disadvantages together also. Now, as you see, the first advantage is this. In the case of high voltage DC transmission, the insulation requirement is less. That is due to the fact that in the case of AC, though power is transmitted due to the RMS value of the voltage, but actually the insulation is provided up to the peak value for the peak value of the system voltage. But in the case of DC, RMS peak, everything is same. So the insulation requirement will be less. This is the first advantage. Next thing is this, for the same peak stress, there is more corona loss and radio interference in AC transmission than in DC transmission. So, corona we shall discuss in the next chapter. When we shall discuss corona, then you will see that the power loss in corona or power loss due to corona will be more in AC than in DC. Now again, when power is transmitted through cables, now for densely populated areas like cities and other places, normally the overhead power transmission is not preferred. The preferred mode of power transmission is your through the cables. Now, when the power is transmitted through the cables, always DC transmission is preferred because in AC there will be continuous charging current and losses thereof, but in the case of DC, there is no continuous charging current. Therefore, for cable transmission, DC is always preferred. Now, another thing you all know, I think you are all used to the term skin effect. What is skin effect? Can anybody say?
It is the phenomena mostly observed in the AC uh, transmission when the current flows to the surface or we can say periphery of the conductor and net current at the core remains zero. This phenomena is
Yes, that
skin
is
effect.
due to the frequency of AC transmission or AC power supply. In AC supply, some frequency is involved. In the case of power frequency, it is 50 hertz in India. So, due to that frequency, initially current starts to flow through the surface, not deep inside the core, and that effect is normally known as skin effect, which causes some problem and losses in the system. But in DC, since there is no frequency, therefore skin effect is absent. Also in AC, you see there is a system, very simplified system. ES is the sending end generator, ER is the receiving end. In between, there is a line whose impedance is R plus JXA. Now, if ER is the voltage at the receiving end and ES is the sending end voltage and I is the current, therefore the phasor diagram is showing the relationship between, phase relationship between ES and ER. you see the sending end and receiving end voltages, they are not in phase with each other, but there is a difference or phase difference between ES and ER, which is normally denoted by delta or alpha, and it is called or referred to as power angle. And I think you have already studied the expression for for power transmission from sending end to receiving end in terms of sending end voltage, receiving end voltage, and delta, etc. That is ES, ER, XS by sine delta. This expression you must have seen or you are accustomed, na? Do you know that? ES, ER by X sine delta. Have you
Yes,
come
sir.
across this expression? Yes. So you see the power that can be transmitted from sending end to receiving end is limited by the value of angle delta or alpha, which is the power angle. But in the case of DC, since the only drop over the transmission line will be resistive drop, therefore there will not be any phase angle difference between the sending end voltage and receiving end voltage. So that way, the power transmission is not limited by the power angle in the case of DC transmission. Next is a DC line requires no reactive compensation. You must have studied that during AC transmission, due to reactive power consumption at different places, capacitor banks are used to, to give input in the system of reactive powers, etc. That you must have studied, na? Capacitor banks, etc. Have you studied?
Yes, sir.
Okay, so but again, in the case of DC, no such reactive power compensation will be required. Another advantage is this: in the case of AC, synchronization is required. Two AC systems operating at different frequencies or even at the same frequencies cannot be connected just like this and that without synchronizing them with each other. But in DC, no such synchronization is required. And also, when we have to interconnect two DC AC systems operating at different frequencies, a DC link is the only solution. What is done on a DC link is placed in between the two AC systems operating at different frequencies, and what is done on one end, it is AC voltage is converted to DC. On the other hand, it is converted from DC to AC. So DC link is the only solution to interconnect two AC systems operating at different frequencies. And also, now, so far we have discussed so many advantages of high DC transmission. But even then, as we were discussing initially, that even the DC system provides so many advantages. Actually, even today, DC system is not very popularly used during transmission or in the case of transmission. That is because of two major disadvantages. First of all is this: we were talking about interconnecting two AC systems operating at different frequencies with the help of DC link. In order to do that, we must have rectifier at one end and inverter at the other end. Now, these solid state devices actually introduces lot of harmonics in the system. That is one point. And also the volt ampere requirement or MVA requirement is also quite large for these power rectifiers or inverters. So this is one advantage. But the most serious advantage is the other one. That is, now I think you have not studied circuit breakers, na, so far. Have you studied circuit?
No, sir.
No. Anyway, I tell you, in any system, whether it is AC or DC, we have to use circuit breakers in order to isolate the circuits. Basically, a circuit breaker is nothing but a switch, sophisticated switch. In our household appliances, in household applications, the switches, different switches play the same role as that of the circuit breakers. But switches are used to connect or disconnect different equipments like lights, fans, etc., etc. But circuit breakers are sophisticated switch. They can operate of their own under the control and instruction of the relays, and they can make or break the circuits as the case may be. But I tell you that, and I am sure many of you must have seen that when we disconnect any electrical equipment from the circuit, or when we connect any electrical equipment in the circuit, be it light or fan, it is more pronounced in the cases of electrical fans, that when we put them off or when we want to switch them off, inside the switch, a small spark occurs always. Has anybody observed this? Has anybody observed this?
Sir, in the lab, when we connect circuits, then there are sparks a lot of times when we are connecting or disconnecting circuits.
Sparks are there, and these sparks always take place, but at present the switches are made in such a way that from outside it is very difficult to see such sparks. But when we had older versions of switch, it's black switches with knobs, etc., then it was always visible that inside there is a small part. Anyway, that is because of you are actually breaking the circuit, means instantly you are releasing the energy associated in that circuit when you are putting the switch off or making the switch on. So you are changing the energy levels in that circuit. That is why when you are putting the fan switch off, there is a spark. That is, the associated energy is released in the form of heat and light, that is in the form of a spark. Now, it is always preferred that the energy that has to be dealt with during disconnecting any switch should be minimum. And in the case of AC circuits, you see that AC waveforms normally passes through natural zero values at regular intervals of time. And the AC circuit breakers are designed in such a way that they normally disconnect the circuit breaker contacts when the current through the circuit passes through its zero value. Thereby, the amount of energy that it has to deal with will be very small. So that is an advantage, major advantage while developing AC circuit breakers. But in the case of DC, no such natural zero crossing is available. Therefore, you have to force the DC current to zero value by some arrangement. You have to make separate arrangement for forcing the DC current to 0, and then only you can disconnect the DC circuit. Otherwise, the amount of energy that will be involved while making or breaking, especially breaking the circuit, will be huge, and that is not possible. Now, this is the major disadvantage of not being able to generate DC efficient DC circuit breaker or effective DC circuit breaker. This mechanism is very complex to bring the current from its natural value to or original value to zero value. That is a very complicated mechanism, and even today, effective and efficient DC circuit breakers are very rare. Is very rare. This is the main reason why DC circuit breakers are not yet developed efficiently, and this is the reason why DC transmission voltage is not very popular even today. So this is all about high voltage power transmission. If you have any questions, you can ask me. Otherwise, we shall move to our next topic, that is insulation. Insulators.
Sir, what is the significance of DC link? Means how it works while connecting two AC systems at different frequencies.
No, DC link is something. This is another like another transmission line. Now you have two transmission lines, both are AC. Say one is operating at 50 hertz and the other is operating at 60 hertz. So you cannot directly interconnect them. What all you can do is this: you just rectify the AC transmission at 50 hertz level, connect it to the DC line, and on the other end of the DC line, you invert the DC to AC, connect it to the AC transmission line operating at 60 hertz. This is how the two AC systems operating at different frequencies are interconnected with the help of DC lines. And these DC lines are normally referred to as DC links, since it is linking two AC lines. That's all.
Sir, how we are saving the insulation cost in DC while we are having, even though we are having high voltage transmission. So high voltage means we should have a high
Uh,
insulation.
no, high insulation, that is all right. But in AC, if V is the RMS value of the transmission level voltage, you have to provide the insulation for peak value of that voltage. That is V into root 2. So you have to provide insulation for V into root 2. But in DC, RMS, average, peak, everything is same. So if the voltage level is V, then you have to provide insulation for the level V, not for V root 2. That is why you will require less insulation.
Yes, sir, yes.
Now, our next topic will be insulators. Now, actually, we all know that there are two ways of power transmission. One is overhead, and the other is through underground cable. So one is overhead through overhead transmission lines, and the other is underground cables. Now, overhead lines are economical since the main insulation is air. Main insulation is air with use of porcelain and glass insulations. Now, but this porcelain and glass insulating materials are provided at the supporting towers. Now, for cables, we shall discuss in a separate chapter, but for insulators, we shall discuss different types of insulators which are used in high voltage systems in this chapter. Cables we shall take up or we shall discuss in a separate chapter. Now, the first thing, let us go to the next slide, which gives you the diagram of a particular type of insulator, which is called the pin type insulator or pin insulator in particular. Now, this is the metallic pin, and it is screwed inside the body of the insulating material. Let us assume that this is a porcelain insulator. That is, the body of the insulating material is made up of porcelain, inside which there is a groove and thread is there, and the metallic pin is also having thread on its outer surface, through which it is screwed at the inside the body of the insulator, and on the other end to the metallic pin it is placed on the tower cross arm, and there is a groove at the top. To this groove at the top, high voltage conductor is normally passed, but just remember, high voltage conductor are just not just placed on the top grooves, they are placed on the top grooves, and with the help of binding wires, they are tightly placed or securely placed with the help of binding wire, and they are actually there are side grooves which are used for tightly fastening the conductors on the top groove. Now, if we just place the conductor like this without binding them actually on the side grooves, then what will happen? During strong wind, the live conductors will be displaced. So they are always placed, binding them to the binding wires, and normally the side grooves are used for holding the binding wires and the high voltage conductor. Now, here actually this is the body of the insulator. There is a line outside the insulator, a gray line or faint line, which has been named creepage distance. And there is another line, again the color is slightly faint, and this is not a continuous line, but there is a line here, there is a line here, and there is another line here. These lines are actually called the protected creepage distance. Just a minute. আমি একটা ক্লাস নিচ্ছি, পরে কথা বলছি। Now let us explain what do we really mean by the term creepage distance and protected creepage distance. Now the labs are closed. Otherwise, there is an experiment on these insulators in high voltage lab where you have to measure, the students have to measure all these parameters, creepage distance, protected creepage distance, all these things, but that scope is not there right at this moment, so long as the classes are not open in physical mode. Till then, you just have a look on this diagram and get some idea, make some idea about these terms. Now, since we are talking about the insulators, we all know ideally the resistance of the insulator for the flow of, or we can say for the conduction of current, the resistance or the impedance of the insulator should be theoretically infinite. But practically, we cannot make any such insulator for which we can make the infinitely high impedance or resistance of the insulating material. Now you see, if you look at this diagram, there through this top cap, the live conductor will move. So at the top of the insulating material, we have live potential, and to this metallic pin, the insulator will be placed at the tower cross arm, and the tower itself, along with its cross arm, is at ground potential. So between this live conductor and earth pin, there is the insulating material. Yes, it is true that so long as the insulator is working in sound condition, no conduction current will flow from the high voltage conductor to the earth electrode, that is earth pin, to the body of the insulator. It is true. To the body of the insulator, no current will flow. But in spite of our best effort, we cannot make the current from the high voltage conductor to the earth pin, that is the earth electrode or earth conductor, zero, I mean completely zero, along the outside surface of the insulator. And the current which flows from the high voltage conductor to the earth pin along the outside contour or outside surface of the insulator is called the leakage current. It is not possible to make any insulator for which the leakage current will be completely zero. It will be very small, no doubt, but there will be always some leakage current. And the length of the path to which the current will flow from the outside conductor to the metallic earth pin, that is the earth electrode, along the outside surface of the insulator, the length of that path is now called the creepage distance or creepage path, as if the current is creeping through that path from the high voltage conductor to the earth. Is the point clear? What do we really mean by the term creepage distance or creepage path or creepage length? Tell me.
Yes, sir.
Okay. Next, protected creepage distance. Now you see that these insulators are normally used in outdoor service conditions, right? So therefore they are always exposed to severe atmospheric conditions, and also they collect huge amount of dust on their outer surfaces while in use. And also they undergo through different service conditions, as we have just now said. Now, obviously, these on the outer surface of these insulators, during rain, water droplets will definitely fall on the outer surfaces. And these water droplets mixing with the dust accumulated on the outer surface will produce a low resistance path for the flow of leakage current. It will reduce the original resistance offered to the flow of current by the insulator surface. When the surface becomes wet and the water mixes with the uh, dust particles accumulated on the outer surface. Correct. And also, it is not necessary that when there is rain, the direction of wind will be such that it will not, I mean, it may so happen that water drops do not fall on the outer surface of the insulator in the vertically downward direction or parallel to the axis of this insulator. It is not necessary that always the water drops will fall on the insulator surface in the vertically downward direction or in a direction parallel to the axis of this insulator. Depending upon the direction of wind, the water drops may fall on the insulator surface, making some angle with the axis of the insulator. Now, protected creepage distance is that part of the outer surface of the insulator which, according to the definition provided in IS 731, it says that if you illuminate the outer surface of the insulator with the help of light, and if you allow the light to fall on the insulator surface, making an angle of 90 degree with the axis of the insulator, under that condition, the sum total of the distances which will remain in shadow will give you the protected creepage distance. Sum total of those distances will give you the protected creepage distance. The significance of this definition is when raindrops or water drops fall on the insulator, making some angle with the axis of the insulator, some part of the insulator surface will not become wet even if the raindrops fall, making an angle of 90 degree with the insulator, with the axis of the insulator. Though never such things happen that raindrops fall on the insulator surface, making an angle of 90 degree. So even then, if that happens, even then there will be some parts of the insulator surface which will remain dry. That is why these inside portions have been considered while finding out the protected creepage distance. These inside surfaces, not the entire thing. Outside surfaces have not been considered. So if raindrops fall here, that will not be able to make these portions, sections or inside portions wet. Sum total of the distances of these sections will be your protected creepage distance. Now these are the definitions of creepage distance and protected creepage distance. You just go through it, have a look, and if you have any questions, you can ask me. Is that okay?
Yes, sir.
Okay. This figure or this diagram we have already discussed. Next is breakdown of insulators. Actually, and there are two types of uh, breakdowns of insulators. Or in other words, there are two types of failures of the insulator. One is flashover and the other is puncture. Now, flashover or sparkover of the insulation surface, actually, I should say that flashover is not a permanent, normally is not a permanent failure of the insulator. On the other hand, puncture is always a permanent failure of the insulator. That is, if puncture occurs in any insulator, that particular insulator cannot be used further. On the other hand, in the case of flashover, if the cause, if the flashover is not very severe, then removal of the cause for occurrence of flashover may allow the insulator for use again. Now, flashover or sparkover of the insulation surface to the adjacent air connecting those parts, I mean conductors, which normally have the operating voltages between them. What does it mean? It means that flashover is actually, if we go back to the diagram, flashover means the ionization of the air in contact with the outer surface of the insulating material or the insulator in between the two conductors which have operating voltage between them. So for this particular insulator, operating voltage is appearing between this high voltage conductor and the earth pin or the earth conductor. So the flashover means the ionization of the air in contact with the outer surface of the insulator in between the 2 points between which the between the 2 points or between the two conductors between which the operating voltage appears. So truly speaking, it is the failure or ionization of the air in contact with the outer surface of the insulator. It is not the failure of the material of the insulator. Okay. The next point, flashover is the breakdown of the surrounding air. Flashover is not a permanent failure, and the insulator can be used when the flashover stops. But this is the condition, this point is to be noted that, but however, repeated flashover causes a mark along the surface of the insulator. This mark, development of the mark on the insulator surface, this phenomena is called tracking. And when tracking occurs, the surface or the insulator as a whole becomes weaker and prone to breakdown. So this is about flashover. Flashover means, I repeat, it is the ionization of the air in contact with the outside surface, in contact with the outside surface of the insulator, and it occurs between the two electrodes which are having the operating voltage between them. Now, puncture. Puncture is a breakdown of solid insulating material between high voltage conductor and the grounded part. But these occurs through the body of the insulating material, and that is why it is a permanent type of failure. If you look at the diagram once again, here, in the case of flashover, it is ionization of the air outside the surface of the conductor, surface of the insulator. But in the case of puncture, it is the failure of the insulating material through the body of the insulator and between the two conductors which are having operating voltage. So, if puncture occurs, there will be a short circuit between the two conductors through the body of the insulating material. Therefore, it means that during puncture, a short circuit path will be developed to the body of the insulating material. And if a short circuit path develops to the body of the insulating material, that short circuit path will remain, and whenever you want to operate that insulator, direct or conduction current will flow through that short circuit path to the body of the insulating material, and the purpose of providing the insulating material is totally lost, and there will be a dead short circuit between the light and arc path. Now that is why it is said that puncture is a permanent type of failure. Now, next point is also very important, that insulators are so designed that flashover voltage is always lower than the puncture voltage. This is done because if the puncture voltage is made lower than the flashover voltage, then always puncture will occur before flashover in the event of any abnormality or abnormal behavior of the system. But if puncture voltage is made lower than flashover voltage is made lower than the puncture voltage, then what will happen in the event of any abnormal condition developed in the system? What really happen will, before puncture, flashover will take place in the system, and whenever there will be some flashover in the system, it will give an indication that some abnormality, the system is not behaving normally, some abnormality in the system has developed. So it will give us that we should take remedial steps, and after the fault or abnormal conditions are removed, then the system can be safely be used. But had the puncture voltage been lower than the flashover voltage, then this opportunity we could not get. Now again, there is another diagram in connection with the pin type of insulator. It is showing that normally what happens, the flashover voltage during rain, or that is, in other words, when the surface of the insulator is wet, under that condition, the flashover voltage is lower than when the surface is not wet, or in other words, surface is dry. Now this is because in the case of dry condition, it is, as it is mentioned, during dry condition, the flashover takes place only through the shortest air path, whereas in wet condition, it would be partly through air and partly through the wet and conducting insulator surface. Now here it has been shown three leakage paths. A is the leakage path, complete leakage path. B is the dry flashover path through the air like this. It will be like this. From there, there will be a jump. It will come here. It will flow from here and finally go. For C, it is again, you see, it is partly through the surface, like the leakage path. But here, in the case of dry flashover, since it is taking place through the air, the path will be, length of the path will be more. And when the length of the path is more, then obviously it will take place, or the flashover will take place at a higher voltage, because you have to ionize air over a longer path. But in the case of wet flashover, since the entire path is not through the air, partly through air, partly along the wet surface, providing low leakage resistance, so therefore it will have to ionize less number of, it has to ionize air to the lesser length of path, and that is why the magnitude of the wet flashover voltage is less than the dry flashover voltage. So, with this, we conclude our discussions today. If you have any questions, you may ask me. And next class, I shall communicate to you. Most probably, it will be same time in next week, same day. But anyway, I shall confirm. And another thing I tell you that when a particular chapter is completed, then the notes on that chapter will be sent to you. But after every day's class, before the next class, recording of today, previous day's class will be sent to you. Is that okay?
Yes,
Yes,
sir.
sir.
Yes.
Okay, then